Hi guys, today I'm going to do the worked examples from 3.7, which is inverse functions. So we've already done 3.6, which gives us a bit of an introduction to inverse and how they work. And there are 4 examples here. So the first one, worked example 11, we're looking at a parabola. Here it is. And we have to find the rule for the inverse. So you probably remember from year 11 that to find the rule of an inverse, we swap x and y. So I'm going to do that. That means y plus 2 squared equals x, and then I can just undo it. Y plus 2 equals plus or minus root x, and then y equals negative 2 plus or minus root x. So this would be our rule, and this is a relation, and it's not a function because, well, the original is not a one-to-one function. So a parabola that's not restricted is never a one-to-one function. It's a function because we cut it once when we do the vertical line test, but if we do a horizontal line test, we cut it more than once, in this case twice. So it's not a one-to-one function. Therefore, the inverse is not a function. It's a relation. And look, if we want to be particular, this correspondence here would be many to one. And it's many to one because you have many x values that give you the same y value, well, namely 2 x values that give you the same y value. So just say this y value is 10, then you'd have this x value and this x value that give you that 10 there. So it's a many to one. That means that our inverse would be a one-to-many relation. So this is a one-to-many relation. Right, so find the rule for the inverse. We've done that. And indicate whether the inverse is a function or relation. It's a relation, and give the domain and range for both. So let's see. In the last video, I pointed out to you that the domain and range swap from the original to its inverse. So the domain here is R, and the range is going to be from 0 to infinity. And that means that for our inverse function, the domain is going to be 0 to infinity, not infinity to 0. So of course that sounds ridiculous, or not negative infinity to 0. Just be careful, you're not swapping these over. No, you're just swapping the domain and range over as they exist. And the range is going to be R. So this one was our y equals x plus 2 squared. And this was the inverse. So we've done all parts of that. Let's move forward. And now they're putting it into function notation, and where it says fully define the inverse, well, that means we need to use function notation. So essentially, as you know, the function notation, we give the name of the function. F negative 1 is the name of the function. Oh, those dots are a bit weird. Where the domain maps into the real number field, where f neg 1 of x equals, and there's the rule. So essentially we need the rule and we need the domain of the inverse. So it doesn't really matter which one you find first, but I'm going to find the rule. So for the rule, we say let y equal f of x, and for inverse, swap x and y. So therefore, x equals y squared plus 2. So let's rearrange. Y squared equals x minus 2, and we're going to root both sides. Y equals plus or minus root x minus 2. So this will be our rule. It'll either be the plus or minus, because remembering that for a function to exist for the inverse, the original has to be a one-to-one function, and we have restricted that. So in a minute we'll look at how that works. I'm just going to write that rule in as it is, and then we can delete the plus or minus accordingly once we know. So plus or minus x minus 2. So there's the rule. Good. Now let's go to the domain and we'll look at the range as well. We'll look at both. So our original function, x squared plus 2, it looks like this. And well, we've cut it. Here's a 2, and it goes from 0 to infinity. So actually what we only want is this part. And the 0 is a hard bracket, so there's a square bracket there. So we're going to include that as a solid dot here. So there's that. So that's how that looks. That's our original f of x. So the domain of f is going to be from 0 to infinity, and the range of f is going to be from 2 to infinity. So this means that the domain of our inverse is going to be the range of f. So remember the domain and range swap. So I can just put that straight in there. There we go. So from 2 to infinity. And the only leftover bit to do is to decide, well, are we using the positive or negative part of the root graph there? So let's see. We know that our root graph, so our inverse, the domain is going to be from 2 to infinity, and the range is going to be from 0 to infinity. So if I think about that, the root graph, the plus and minus part of it, is going to look like this and like this. And the domain doesn't tell me, the domain is the same for both, but the range, that gives me some important information. It tells me that it's the upper part of it. So it's the top bit because the range is from 0 to infinity. So it means it's the positive section of that root graph. So I'm going to delete the minus, and look, I'll delete the plus as well, because obviously you don't need to put a plus there if it's positive. So this would be our fully defined rule, or our fully defined inverse function there. It is written in function notation. It includes the domain of the inverse and the rule of the inverse. Let's move forward, and these ones are a little bit more detailed, I guess you could say, asking us to do a few extra things. So firstly, we're asked to find the rule for the inverse and explain why the inverse is not a function. So I already can say that it's not a function because our f of x is not a one-to-one function. So that's going to be the reason. But let's find the rule for a start. So let y equal f of x. For inverse, swap x and y. Therefore, 2 minus y squared equals x. And then, well, negative y squared equals x minus 2. Let's divide everything by negative 1. And then let's square root both sides. Plus or minus 2 minus x. And of course it's a plus or minus, and you really got to know that by now. You know, when you square root something, you've got plus and minus values. So we need to choose what's more sensible. Well, not yet. They're just asking us to explain why the inverse is not a function. So this is a relation. And it's a one-to-many relation. If we want to be, really specific there. Up the top, our parabola, our f of x function, if I draw that, that looks like this. And, well, this is a many-to-one. Notice that if that's a many-to-one, then our inverse has to be one-to-many. So again, they swap over. It's many-to-one, again, because you have many x values that give you the same y value. Really just 2, but, well, we say many. So just say that's a 3. Then our x values could exist here and here, or do exist there and there. So there's 2 x values that give you 1 y value. That means it's a many-to-one function. So a many-to-one function will not have an inverse. Only a one-to-one function has an inverse. Or has an inverse that is a function, I should say. Only a one-to-one function has an inverse function. So you can still find an inverse relation, but you won't get an inverse function. So if the domain of f is restricted from negative infinity to a, so it must be like this, find the maximum value of a, so the turning point value, so that the inverse exists. And we can see really quite clearly that the x value is 0 here. So for part B, A equals 0, and that means that our domain of f is going to be restricted. So the domain of f is going to be from negative infinity up to 0. And actually, I should be careful here because this is a soft bracket. So this means that actually in my picture there, now it's going to rub out the whole thing. Not too bad. There we go. It means I need an open circle here. So this is the part I want. Actually, I might get rid of that. So now this is no longer a many-to-one function. This is a one-to-one function. So for every y value, you're going to have one x value. So for every x value, you're going to have one y value, I should say. Always say the x first. So we've found the value of a. Now we have to sketch the graph of f of x over the restricted domain. We've done that. And use this to sketch its inverse on the same diagram. Okay, so we know that this value here is 0, 2, I believe. Yes, yeah, of course, 0, 2. So if that is our turning point on the parabola, then the starting point for the inverse function is going to be 2, 0. So we're swapping x and y. And inverse, well, what happens in an inverse is we reflect over the line y equals x, and mine's not really to scale, so it won't be perfectly looking like a mirror image there, but it should look like this. And the two of them will intersect on that line, and this mirror image line, or the mirror line, is y equals x. So this would be our inverse sketched on the same graph as the original f of x. And notice also that I've done the open circle for both of those because of our a value having a soft bracket there. Okay, so we've done C. So let's go for D. Form the equation of the inverse y equals f neg 1 of x. Okay, so part D. So we've already found we've already found the inverse relation there. We've found the rule. So then, well, we don't need to do that all again. We can say f neg 1 of x is going to be, and we choose which one is the relevant one, and we can see that it's the negative. It's going beneath the graph there, it's the negative. So it's going to be our negative root 2 minus x. So, lastly, at what point do the graphs intersect? And this is the bit where on exams and SACs, people don't do this quite so well, because people try and equate f of x to f neg 1 of x. So f of x equals f neg 1 of x. That is where it intersects. So you're right. But the equations we have there, so f of x is 2 minus x squared, and f neg 1 of x is negative root 2 minus x. Well, this is really quite hard to solve, so you don't want to do that. What we need to understand and see is that they also intersect with the line y equals x. So that means that you can choose one of the equations and just equate it to x. So look, I'm going to choose the quadratic, 2 minus x squared, and that equals x. And then, well, 2 minus x squared minus x equals 0 gives me, well, let's put it on the other side so they're positive, x squared plus x minus 2 equals 0. And I can now just, do cross multiplication, which gives me 2 times neg 1. So neg 1x plus 2x equals 1x. And yes, that is our middle term. So our intersection points, we're getting two values for x, and we'll talk about those in a second. So x could equal neg 2 and x could equal 1. So we need to look and see, well, what's going to be the one that works. So x is either 1 or negative 2. And if we look on our graph, we can see, well, it's not going to be, let me just go back to that 1. It's going to be that they intersect at negative 2. So if we had drawn our other part of the graph, then yes, they would be intersecting at 1. So you have another point of intersection there if we were talking about the inverse before we restricted the function of f of x. So you can see that this value is a negative, and you can see it's negative 2. And well, to find the y value, this line is y equals x. So if x is negative 2, y is also going to be negative 2. So our intersection is at neg 2, and they will always be the same. So if your x value is negative 3 root 7, your y value is negative 3 root 7. Whatever the x is, the y is for our intersection point of the inverse with its original function. So that completes worked example 13. Let's go to the final one, and it looks like it's going to be fairly similar to what we've already done in worked example 13. So consider the function f where it's this quadratic here. So find the largest value of a so that f neg 1 of x exists. And as we've seen, what's important for the domain, for our restricted domain, is the turning point. So let's find that, and it looks like I'm going to have to complete the square. So let's let y equal f of x from the very start, and that way if we write y, we're already covered. Y equals x squared minus 6x plus half of negative 6 is negative 3. Negative 3 squared is 9. Let's minus 9 and add 4. So y equals x minus 3 squared minus 9 plus 4 is minus 5. Okay, so this will be our quadratic here, and of course that would look like 3 neg 5, something like this, with the turning point of 3 neg 5. And what we see is if we want to restrict this and go from negative infinity, then well, we're going to be cutting off that part. So our value of a, the largest x value we can have for a one-to-one function, then a is going to equal 3. So our new domain of f, may as well write it in straight away, is negative infinity to 3. And well, why not write the range while we're at it? So the range is going to be from negative 5 to infinity. All right. So we found the largest possible value of a, so 3, that's all you have to write there. I just added the domain and range, so it's just a little bit, so we've got it there, so we can use it soon. Now, let's see, let's get a new color. So find f neg 1 of x and sketch both graphs on the same set of axes. So we've already let f of x equal y, so I'm going to say for inverse, swap x and y, therefore I'm going to use this because I'm going to be able to undo that far better than if I'm going to use this. In fact, I can't undo that as it is, so in turning point form it's quite nice. So therefore y minus 3 squared minus 5 equals x, and let's undo. Y minus 3 squared equals x plus 5. Let's root both sides. Y minus 3 equals plus or minus root x plus 5, and then y equals plus or minus root x plus 5 plus 3. So this is my my inverse, and I've got to decide whether I want the positive or negative part. So I'll do that by, I'm going to sketch them. I'm going to have to sketch them anyway. So the first one is f of x, so I'll put that here, 3 neg 5. And we've already said the domain and range of it up the top here. So now if I want to sketch the inverse, well, the inverse, the domain of the inverse is going to be the range of the original, and the range of the inverse is going to be the domain of the original. So we know that our starting point of our root graph here is going to be at neg 5, 3, the opposite of this. So I could either look from the rule or I could just swap around my x and y values there. So negative 5, 3, so let's say it's somewhere here. I'll try and make it more mirror image. Let's say it's here. So it's either going to look like this, or it's going to look like this, and that's what I need to decide. You can probably see already which one it's going to be, but let's still work through it. So the domain is not going to be helpful. So the domain of f neg 1 is the range of f, which is -5 to infinity. And the range is the same for both of those parts of f neg 1 of x. The range of f neg 1, well, that's going to be the domain of f, and that's -infinity to 3. And that's helpful because, well, if we're going from -infinity to 3, it's clear then we've got to use that one, not this one. So let's delete that part, and it will look like this. Actually, I might just draw it a little bit more nicely. I'm going to put my y equals x line in, because then I know that I'm going to intersect here, and it will look something like this. So it's my mirror image. It intersects on the line y equals x. So that means it's the negative part, and it means that this is going to be my rule. So let's change the y to f neg 1 of x, because that's what we've been asked to do. Find f neg 1 of x. So f neg 1 of x, there it is. And we've sketched them both on the same axes. So the last bit is to find the points of intersection. And again, we must really think that the point of intersection will be between all three lines. So between the blue one, the purple one, and the orange one, which is y equals x. And y equals x is really easy to use. So we always will use that rather than equate the inverse with its original. So I'm going to take the parabola. I think that will be easier to do. So x minus 3 squared minus 5. And I'm just going to equate that to x. So I'll expand this. X squared minus 6x plus 9 minus 5 equals x. X squared minus 6x minus 1x is minus 7x. 9 minus 5 is plus 4. And look, this one actually is a little bit more involved than I would like, because you're not going to be able to cross multiply it. So we're either going to have to complete the square, which would involve halving this odd number, which is not very nice. So quadratic formula will be the way to go. So our x values of the intersection is going to be -b plus or minus root b squared minus 4ac over 2a. So let's do it. -b plus or minus root b squared minus 4 times a times c over 2 times a, which is 1. All right, let's continue. 7 plus or minus root 49 minus 16 over 2. So that's 7 plus or minus root 33 on 2. So root 33, we can't break that down. So this will be our final answer, but be careful because, well, these are two values here. So actually I shouldn't say it's a final answer. We have to choose which is appropriate. So there's a positive, so 7 plus root 33 on 2 or 7 minus root 33 on 2. So if we think about root 33, well, that's in between root 36 and root 25. And so it must be between 5 and 6. So 7 minus 5 or minus 6 is still a positive number. So both of these x values will be positive. So that's one thing to note. Let's see which one is going to be suitable. 7 plus something between 5 and 6 or 7 minus something between 5 and 6. So I'm going to go back to the picture then. And, well, 7 plus something in between 5 and 6, that's not going to work for us. And actually my graph doesn't look too good there, does it? I know why. Because you see I have a negative. Actually I should put them back and I'll explain that. So if I had this value here as my intersection, it means my x and y values are both negative. But we just said that the 7 plus or minus root 33 on 2, they're both going to be positive values. So for a minute there I was a little bit confused, but if I had drawn this a little bit more carefully, then what we would see, it must be that the parabola goes like, that's not very nice, like that. And then, well, here's going to be my intersection, and my root graph is going to go like this more. So I just drew it in such a way that neither of those intersection points made sense. But now I can see clearly, well, it's positive, and the 7 plus root 33, well, that's 7 plus something in between 5 and 6. So even 7 plus 5, that's going to be 12 divided by 2. That's going to be 6. That's going to be bigger than what this domain will allow, the domain of my purple original graph. So it means that it must be that the point is 7 minus root 33 on 2. And of course, x equals y, or y equals x. So it's going to be the same value for both. So a little bit of thinking on that one if you're doing it by hand, because you really have to consider what 7 minus root 33 on 2 actually is. Is it a positive number? Is it a negative number? Which of those, the plus or the minus, is going to be most sensible as well, which is going to work as the intersection. So I think that is actually it. So yeah, that's the points of intersection, and yeah, that completes the worked examples for 3.7.